So I've opened up the first of the projects. I'm just using Visual Studio Code here, but you can build it in the terminal using CMake and the standard build tools that I use. It should also run in Mac and Windows. There will be a few demos that will not work under Mac, and sorry, Linux, not Windows. So we'll start with main. So main is a standard Q GUI application. We build the Q GUI application here. For the command line parsing, I thought I'd investigate Qt's process for doing command line parsing, because we're writing a Qt app, it makes sense. So Qt has a module called Q command line parser, and we set up a parser object, do the description, and then it gives us the ability to add our options. So as you can see here, my option is -h and minus height, and there's some text to say what the values are, and then it's like a key value pair for the variable name that we're going to search for and the default values. So I've got width and height set to default of 150, and I've got the number of particles set to default 200. We then, when we want to parse this, we basically get the variable width parser, search for the key, convert it to an int. So you can see those values come through with the default values unless I pass something else. So it's a really quite a simple process. It's rather nice. Next, I'm going to set up my default OpenGL version. So we target 4.1 on the Mac, 'cause it's the highest version we can do under Mac OS X. At the moment, I've 4.3 here, but actually we can go up to 4.6, I believe, in the current drivers that are here. We then construct our NGL scene window and of course show pass control to Qt. As with all my demos, if you want to look at this sort of structure, look at the rest of the lecture notes and so on. So our NGL window has the usual stuff. We construct the NGL scene. I'm storing the grid width and height as parameters, storing the number of parameters. There's this variable here called update time, and update time is, let's just load the element here, is just a dequeue of type long. And what I'm doing here is I'm pushing to the back of the dequeue, popping from the front of the dequeue once it gets to a certain size, so that I can average the time samples that I'm taking for the update time, because I was finding it was flickering so much it was really hard to do. So I'm taking a sort of rolling average of the update time there. And obviously, to stop a division by 0 first time we run, we just need to put a dummy value in. So you will notice when the program runs that the update time will settle eventually onto a smallish value. If we just run the program here, we should see that value sort of settles through. I've got it in debugging mode at the moment. I'm just going to stop that and we'll come back to that in a little while. We've then got, so NGL scene is doing some basic setup. It's calls the initialize GL the first time the window's created to do all of our basic initialization for OpenGL. So I'm initializing my NGL library, setting up some parameters. So I've got a basic camera that's just looking from above, so I take the highest grid size and use that as an offset with a little bit to move the camera so we can see however size we've got. I'm doing a perspective projection here. Really, I might modify this later to do sort of more orthographic, because I think this is where a lot of the issues with the clipping of the lines is coming in. I'm loading my shaders. I'll discuss the shaders in a little while, but in this case I'm using a vertex shader, a fragment shader, and a geometry shader. I'm passing in a point and a direction, and I'm using the geometry shader to draw a line based on that, because that's a fairly quick way of doing things. And then I'm just creating my grid class, which is where all of the simulation works. The paint loads the model view project matrix to the shader, so everything gets multiplied by that for doing the visualization. I take a clock time for the drawing begin, and then I call grid draw, take the end, and then I print that text up onto the screen. The draw time is fairly stable. so we don't get much of a bottleneck for doing the visualization of that timing. So I'm not doing the rolling average for it. It's the update, especially with some of the early ones that get the cache misses and so on, which makes it harder to see. And my update, so we've got the ability to toggle things being updated onto a key. So you press the space key and it will toggle the update up and down so you can see what's going on. And I call grid update. Again, at the moment, all of the demos are using a fixed time step of 0.01 float. What we'd actually do is measure the time between update events and calculate a better update time. But for now, it just makes it easier for doing comparisons if we do a fixed time stamp. The other thing with this is, so the timer event is triggered every 20 milliseconds. And you will notice that in this case at the moment we're going through every 20 milliseconds update will be called, but draw is locked to the vsync, so the draw is only being called every so often. One thing we'll see later is that does have a implication to how we update OpenGL and update our simulation, but we'll talk on that in a later demo. And the drawing itself is handled in the grid class. So in this simplest of demos, what we've got here is a simple structure called particle. It's passed in a position and direction, and it's also got an acceleration and a max speed value. And grid.h is going to have a stood vector of particles. So it's an array of structures, this data type. Grid is constructed with a width and a height and a number of particles, has methods to draw and update. It has a method to return the number of particles, and then private initializing grid, reset grid, width and height. And we're using my NGL-VAO classes for doing the drawing and the visualization. So again, let's have a look here. Construct the grid. We're going to create a multi-buffer VAO for our points. We have two buffers, one which is going to contain all of the XYZ coordinates for the points, another buffer for the direction vector. Those will get passed through every frame and ingested by the vertex shader, passed on to the next stage for doing all the drawing and so on. And when we draw, basically what we're going to do is we are going to loop through. We've got a vector here. We're going to push back our position and our directions. This is slow and deliberately slow. It's a very naive way of doing things, but it's done this way. We're binding our vertex array object. We're setting the data. Setting our vertex attribute pointer to say the first input is the particles, the positions, the second one is the directions, and then we're calling draw and we're unbinding. So incredibly inefficient, but as you've seen already, we can do 10,000 fairly quickly. But I've deliberately done this quite inefficiently because the first thing we're going to do is improve the drawing speed. And then the update simulation is a very, very simple simulation. As I say in the write-up, we're doing an embarrassingly parallel simulation here. We are literally, each particle doesn't need to know about any of the other particles. It only needs to know about the full walls, so we're going to do a quick bounce off the walls, but that's it. In a future post, I will look at how we can do more efficient simulations where particles need to know about each other and other objects in the scene and so on. But for now, we want to keep this simple just to show the principles of what are going on here. So for each particle, grab the particle. Notice it's by reference here because we are going to mutate that particle. And I'm saying direction equals the current particle's direction multiplied by an acceleration vector. I'm negating the zero component here because I'm just visualizing in 2D. If we're doing 3D, then obviously we just use it. And I'm visualizing for ease across the X, Z plane, and then I'm viewing from above. It just makes sense to do it. I'm clamping this direction by the max speed so that we don't go too fast when we do this with the time step. And then I'm adding that direction to the speed. I'm saying if the max speed gets less than 0, reset the particle. And then I'm doing my collisions with the walls. This is incredibly brute force. I'm saying if my x position is less than the negative x size of the grid that my width and my height, then call reflect. Reflect is a built-in function with the NGL vec3, but it's basically given a normal, calculate the angle of incidence, and then you just do the reverse angle out. And I just take a little bit off the speed, and that's set for each object. Same with the right plane, the top plane, and the bottom plane, and that's it. And reset particle just sets the initial position to some value between width and height, positive and negative random numbers there. The direction is a random vector 3 multiplied by 2 to give it some extra speed. Maximum speed is a random positive number between 5 with a 0.1 on there, just so it's got a little bit of initial impulse, and acceleration, same sort of thing. And that's it for that. So we initialize the grid, set off the simulation. Every frame we update, calling update, and that's doing the simulation. And we're going to keep that same simulation all the way through. What we're going to do is make that simulation more efficient each time we go through. We've also then just got the shaders here. So my vertex shader in this case is passing in input position, input direction. We are outputting the position by multiplying it by the modeling view project matrix. We're also multiplying the vector by the modeling viewing projection matrix, because we want to visualize that vector by basically pushing along that vector the point that we've currently got to give us a line to draw. That gets passed into the geometry shader, and as you can see, my geometry shader is just emitting the vertex for the first position, setting a color, emitting the vertex, and then moving along from the current position along that vector that we've passed in, emitting the second vertex. So you'll notice that we've got points being put in and a line strip with 2 vertices, so a single line output. And then the fragment shader just draws the current color value that we've passed out from the geometry shader. So it's the simplest shader we could do. There's no real sort of processes there. So that's the basic structure of the demo. What we'll do next is we will fire this demo up in the debugger and have a look at any performance hotspots that we can see.